Happy New Year, everybody. It is my absolute pleasure to introduce the first speaker of Champ 2022. Kevin Harris from UT Arlington will tell us about decompositions of modules over principal subcategories of truncated polynomial rings. Kevin.
Thank you so much. All right, can everyone hear me? Okay. Okay, awesome. Thank you so much. So yeah, thank you for inviting me to speak. I'm delighted to be the first talk of 2022. So hopefully I can bring in the new year right and start off on a good note. I'm going to try my best. So yeah, as mentioned, my talk is over the decompositions of modules over principal subalgebras of truncated polynomial rings. I'll sort of explain what all that means as we go forward. So just sort of an outline of what we're going to talk about today. Just kind of set up the background. Then we're going to talk about, we're just going to sort of mention the decomposition theorem for PIDs and why that's for modules over PIDs rather, and why that's important to our research, to my research. We're going to talk about what are representation matrices and why they're important. We're going to refer to something called the Clebsch-Gordan problem, which if anyone's done any like Lie algebra work or whatever, that's something that may sound familiar. You might have heard of the Clebsch-Gordan formula or the Clebsch-Gordan coefficients or something like that. But this is sort of a different case that we'll talk about today, and then some results that I have, and then also some future goals. All right. All right, so the background, let's just go ahead and get right to it. So we have we call it A or A and P. Let it denote the following truncated polynomial ring, which is just the polynomial ring, and then you cut out the ideal generated by x1 to the p, x2 to the p, so on and so forth, all the way up to xn to the p. Throughout the talk, you'll hear me just call it A, unless we're talking about specific examples, like you might hear me say A22, for example. That just means that n is 2 and p is 2, or A32 or something like that. But more than likely, I'll just say A for the rest of the talk. K is going to be a field per usual, and the characteristic of K is going to be P for some prime P. Okay, so we're dealing with prime characteristic in our field. Okay, and then we're going to let R equal K bracket U lambda. That's going to denote the principal, this should say principal subalgebra of A, where lambda is going to be equal to the n tuple, so lambda 1 up to lambda n in Kn, and U lambda is just a k-linear combination of those variables of x1 up to xn. Okay, and one important thing we want to note is that in R, we can see that if we take U lambda, so take this, let me see if I can get the draw thing going. Oh, it's interesting because this thing is in the way. And we got it. Okay, so if we take this U lambda and we raise it to the P power, we can see that because of the fact that we have characteristic P, that essentially gets rid of what I like to call all the middle terms per se. And so we're just left with lambda 1 to the P times x1 to the P plus lambda 2 to the P, x2 to the P, so on and so forth. And so, but all of this, since again, K bracket, so R, since it's a subalgebra of A, technically all of this just equates to being 0. Okay, so that'll be an important note for something we do in a couple minutes. Oh, I got to get rid of the draw tool. All right. There we go. Come on. All right, there you go. There we go. All right. So as I mentioned before, just talking about the fundamental theorem for modules over a PID. I guess depending on what book or source you're looking at, it might be worded a little bit differently depending on what you look at. I got this definition out of a book called Steps in Commutative Algebra by R.Y. Sharp. I don't know if everyone can see it. It's like a blue book. That's where I got my definition from. It's one of the first books I started reading when I started doing research. And so I'm not going to really read it, but this is one of the biggest theorems that we'll use, that we use throughout my research. And the reason it's because we basically want to take this theorem and see if we can apply it to sort of a principal ideal ring, but a very specific one. Okay, so what we do is we take the ring k bracket x mod out x to the p. So we take a truncated polynomial ring, but instead it's just in one variable. Okay, so basically a1p, if you want to think about it like that, right? And so just think about how we have a natural epimorphism from k bracket x to k bracket x mod out x to the p. And so this means that any k bracket x mod out x to the p module can be regarded as a k bracket x module. And so since that happens, we have a we can have a decomposition for that module based off of the decomposition we just talked about, based off the fundamental theorem. And so once we do that, then we basically take this decomposition that we have and we try to see how we can basically transfer it over when we regard M as a k bracket x mod out x to the p module again, because that's where we started originally. And so to do that, what we do is, well, when we decide to view M as a k bracket x mod out x to the p module, then we have that ideally, that means x to the p should kill the module, right? If I take x to the p and multiply it, if I take the module and multiply it by x to the p, that should kill everything. And so when we look at this decomposition, in order for everything to kind of follow suit, that means that, well, for one, we need the free part to basically just not be there, right? We need the k bracket x, the copies of k bracket x or the copies of that ring to not be there. So we need that to just disappear essentially. And we also need something very particular to happen with these irreducibles, okay, with these P1s up to PMs. So, and we can see that in order for everything to be zero like we need it to be, well, that just means that x to the p has to belong to each of these ideals. But of course, that just means the ideal generated by x to the p has to be a subset of those ideals. But we can use radicals to show that that just means that the ideal generated by x has to be a subset of the ideal generated by p sub I, which lets us know that the two ideals are actually going to have to be equal, because it also follows that since p sub I, since these p's are irreducibles, the only way that can happen is if let me try to use this draw tool again. Thing keeps popping up. I wonder if I can do it on here instead. We get that p sub I also has to All right. Sorry about that, guys. Again, off to a great start for 2022. So no, like I was saying that we have that the ideal generated by x has to be a subset of the ideal generated by p sub I based off this argument up here. And then we have that since the ideal generated by x is the lone maximal ideal of this particular ring, that it follows that each of these p sub i's, or the ideal generated by those p sub i's, also has to be reversely a subset of the ideal generated by x. So then we get that those ideals actually have to be equal. Okay. And so what that does for us, there we go. Sure, nothing's missing. Okay. So what that does for us is it gives us sort of a decomposition theorem for this particular ring. Okay, for k bracket x mod out x to the p. Okay, let me move this up a bit. Okay, and so what we have is let M be a finitely generated module over K bracket X mod out X to the P, and D sub I equal K bracket X mod out X to the I for any I in between 1 and P. Okay. Then we have that there is going to exist non-negative integers M sub I, where i's run from 1 to P again, such that M is going to essentially break down into these indecomposables, all right, where you have K bracket X mod out so many copies of K bracket X mod out X, so many copies of K bracket X mod out X squared, so on and so forth. But notice it goes up to a certain point. It goes up to P and then it just completely cuts off. It can't go any higher than that. And that's simply because of the fact that we're truncating our original ring, we're truncating at P. We're not going any higher than that. So the decomposition kind of follows suit and only cuts off up to a certain extent. Okay. And so one question people might ask is looking at it, some people might look at it and say, oh, it's right there. Other, it might not be as obvious, is, does this decomposition have a quote unquote free part, right? We have our torsion parts and we have our free parts. And so where exactly is the free part? And basically what all this says, this is just sort of an argument basically to tell you that the free part is just this part right here. Okay, because all this part is, it's exactly what this is to a certain degree. Okay, it's just K bracket X mod out X to the P, right? It's essentially the same thing as the ring. Okay, and so everything else below that, P minus 1 and going below, is just the torsion part, but we have our free part right here. Okay, and so another thing we want to point out is that this is that last part. I guess I should circle the DP too, but that part is isomorphic also to K bracket U lambda. Again, kind of following from the argument up here. And then also we have that each D sub I is actually going to be isomorphic to K bracket U lambda mod out U lambda to the I, really just sort of from a change of variables, right? Instead of X, you're using U lambda. So similar idea. Let me know at all if I'm ever going too fast or anything. All right, so all right. So one question we like to ask is, if we have some finitely generated A module, M, then pending, of course, K is infinite, we have infinitely many choices for our lambda, so for our n tuple. And basically we want to understand is, how does the decomposition of M change as lambda changes? And hypothetically, does the decomposition always change, right? So you could have examples where the decomposition will change depending on how you change these lambda sub i's. And we could have an example or some examples where the decomposition didn't change at all. So let's sort of look at that, take a look at a couple of examples. So let's look at A22, right? Two variables, and then mod out to the second power. Okay, so if we consider the ideal generated by x1 of A, right? Just take the ideal generated by x1. Clearly, of course, I is going to be an A module, so we don't have to worry about that. And we can see that I is actually going to have the following K basis, x1 and then x1, x2. So it has these are its two basis elements over K. Okay, we just want to recall that R, so the K bracket U lambda is going to be the subalgebra of A, the principal subalgebra of A rather, where U lambda is going to be equal to lambda 1 x1 plus lambda 2 x2, where of course lambda 1 and lambda 2 are both in K. So again, just recalling what U lambda is. And we want to suppose, let's just let lambda 1 equal 1 and let lambda 2 be 0. Then by that definition, by a definition of U lambda, R is just going to be equal to K bracket x1. Okay, and so then we want to figure which, what would it need? What would I need? What generators would it need to, or what elements would I need to generate as an R module? Okay, and so since we're looking at R equals K bracket X1, it would still need X1 and X1, X2. It would still need to start off with X1, and then there's nothing in R that's going to help us get X1 and X2 from X1. So we're still going to take those two original basis elements because we know that we can get all of K in here. So if we just take these two, we'll be fine. Okay, so we have that I, and then everything follows suit for it to be a direct sum. Everything's I think it's uniquely written. So you have Rx, so you have I is going to equal direct sum of the ideal generated by X1 over R and the ideal generated by X1, X2 over R. And then we can go through this process with, looking at the annihilators and to see that this is all just going to break down to 2 copies of K. Okay. So then let's see what happens if we decide to flip it, right? Let's see what happens if we decide to let lambda 1 equal 0 and lambda 2 equal 1. Then we have R is going to be K bracket X2. So it turns out that I actually only needs 1 generator to generate as an R module. Okay. And that generator, we can go ahead and take to be X1. Okay. Because then if we take that to be X1, of course, we can get X1, X2 by just multiplying X1 by X2. So that works out nicely. So then we have that I is just going to be equal to Rx1, which of course is just going to be isomorphic to R mod out its annihilator, which the only thing that annihilates X1 from R is just going to be 0 because no form of X2 is going to annihilate X1. So then basically we go through all this just to see that I is going to be isomorphic to R. So just a copy of our K bracket U lambda in this case. So we see that not only do the decompositions change, right? We have over here, it was 2 copies of K. And then over here, we have a copy of R. So not only do the decompositions change, but with the quote unquote right conditions on R, on lambda rather, with the right conditions on lambda, we can see that I can also be viewed as a free R module. Okay. So let's look at another example. Let's say we're going to use the same truncated polynomial ring, so A22, so 2 variables and mod out the second power. And we're going to let I represent the ideal generated by X1 and X2. Then we get the following K basis, which is just X1, X2, and then X1, X2. Excuse me. Then we're going to sort of do the same method. We're going to look at what happens if we let lambda 1 equal 1 and lambda 2 equal 0, and then we're going to flip them and see if anything changes. So with R equaling K bracket X1, we get that we need 2 generators. So yeah, with lambda 1 equal 1 and lambda 2 equal 0, we get that R is equal to K bracket X1. So we get that I needs 2 generators. And so we can take these 2 generators, be X1 and X2. And so we're going to have that going through this process. We get that I is going to be isomorphic to a copy of K, direct sum with a copy of the ring. Okay, so K and R. Okay. If we decide to flip the conditions, so if we let lambda 1 equal 0 and lambda 2 equal 1, so that R is now K bracket X2. So we still see that I is still going to need 2 generators to generate as an R module. And of course, we can go ahead and take those generators to be X1 and X2. There's no issue with taking those same generators. So, but we can also go throughout this process. Again, it's a very similar process. And it kind of works similarly. It's just everything sort of switch places, right? There's one thing that turns into K, and then there's one thing that's just R, and then sort of the same thing happens over here. It's just in a different order. But of course, we're just direct summing things, so that part doesn't matter. So we still get a copy of R and a copy of K. So in this case, we get that the decomposition didn't change. Okay. So this particular module, So I equals the ideal generated by x1 over x by x1 and x2. We actually get that the decomposition for that particular module is never actually going to change. Of course, the only time it would do something weird is if both lambda1 and lambda2 were 0, but that's something we don't allow because we can't have u lambda being 0. There's nothing fun happens there. So so we have that this decomposition for this particular module doesn't actually change. And so this module, so I would be referred to as a module of constant Jordan type. Right. Now, those modules are great, they're really cool, but but for our research, me and my advisor, we like to look at modules where they don't have constant Jordan type. We like to look at the ones that do change all the time, because then determining those conditions on whether what lambda has to be, it can be real interesting, right? Depending on what modules you're looking at. All right. So let's maybe look at it a different way, and this is what I was concerned about in terms of it cutting off. Okay, I think that's good. So yeah, let's look at the example, the very first example we did. So again, same A, just 2, 2. And we take the first ideal, the one that was generated by x1. And so we determined what that basis was. It was just x1 comma x1 x2. And we want to understand what happens if theoretically, what happens if I take both of those modules, or I'm sorry, both of those elements, and multiply them by u lambda, right? What happens if I multiply u lambda by x1, and what happens if I multiply u lambda by x1, x2? Okay, so if I multiply u lambda by x1, I end up getting just lambda 2 times x1, x2, because I'm going to get a lambda 1 x1 squared, but x1 squared itself is just 0 inside of A. Okay, so that part just wipes away. So we're just left with lambda 2 x1 x2. And then if I multiply u lambda by x1 x2, I actually just end up getting 0, because I'm going to get an x1 squared, which wipes away, and I'm also going to get an x2 squared. I'm going to get like an x1 squared x2, which goes away, and then an x1 x2 squared, which also goes away. So I'm just left with 0. So then what we can do is we can take these calculations and represent them in terms of what's called a representation matrix for u lambda over I. And so what this means is we basically take, in this case, a 2 by 2, because there's 2 basis elements, and we let x1 represent the first column, right? What happens if we multiply u lambda times x1? Let that be represented by the first column, and let x1, x2 be represented by the second column. And so remember, if we multiply u lambda by x1, that gave us lambda 2 x1 x2, which means we're going to get a lambda 2 right in this left bottom corner. Okay, and then of course, if we multiply u lambda by x1 x2, we just got full on zeros, so nothing fun happens. So nothing interesting happens there. So when we look at this matrix closely enough, you can see that it has its rank will change based off of what's happening with lambda 2, right? If lambda 2 is non-zero, I'm going to try to use my drawing tool again. So we can see that if lambda 2 is non-zero, and I'm just going to put R for the rank, then we see that the rank of this matrix is just going to be 1, right? But if lambda 2 is equal to 0, then of course the rank of this matrix will just be 0, because it's just going to be the 0 matrix. Okay, and so one of the things you can kind of, and if you do, I still have to do more examples of this and see if I can sort of generate a proof by it. This is more of a conjecture that when you look at the rank and compare it to what's going on with the conditions on lambda, usually this will sort of tell you basically how many copies of R how many copies of R you'll have in your decomposition. So you see when lambda 2 was 0, when we had that k bracket x1, we just had that I was isomorphic to 2 copies of k. So you see it didn't have a free part. And then, but you see that whenever lambda 2 was non-zero, we got that I was just going to be equal to R. So it actually ended up being a free module. We had the 1 copy. Okay. All right. So there we go. And there we go again. So just in general, with what a representation matrix is, let's see, get this to agree with me. There it is. All right. So if we let M be a finitely generated A module, 227, A module with the following K bases, so let that be its basis. And we suppose that there are going to exist some A sub ij belonging to the field such that all this fun stuff happens. Then we can take a matrix and use that as the quote unquote representation matrix of u lambda on that module with respect to that k basis and represent it this way. And what this does is this allows us to extract a lot more information just by using the matrices, and we can take these matrices and multiply them together and see what we get out of that, mainly, from what the ranks are and things like that. And this allows us to extract a lot more information just by using matrices as a tool, basically. Okay, this gives us a way of representing our module using a matrix. Okay. And so one of the ways we can do that is, since we know that u lambda is going to be this k-linear combination of the variables, then it's going to immediately follow that the representation matrix of u lambda over that module, or u lambda over the module, is just represented as the linear combinations of those matrices. Okay, so it kind of follows pretty much immediately from that. And so then one of the ways you can go about figuring this out, or breaking this down, is to look at each of the representation matrices for x sub I on M. Okay, and we just denote them as x sub I with the M down here. Okay, and so one of the things we want to look at is, well, if we know what x sub I over M looks like and x sub I over N looks like, then what happens? What does x sub I over their tensor product look like? Okay. So let's and so to think more about that, we're going to try to go to a simpler case first. We just want to kind of look at what happens with one variable before we start doing the things with all these other variables, because it gets real complicated real fast. So to do that, let's just say theoretically we just go with one variable, right? And so recall that we had that decomposition we figured out earlier, right? Where each thing just looks like k bracket x mod out x to the I. And then we want to understand what each, okay, just want to make sure I'm reading this right. Yeah, and so we just want to understand what each representation matrix for these quote unquote d sub i's look like. And so each d sub I is just going to have k basis, 1, x, all the way up to x sub I minus 1. And so for this, we don't look at what technically what u lambda does to it, or I guess in a way we do, because once we translate to one variable, all it is that our, oh, I was doing so well, and then the thing got in my way again. Here we go. All we want to do is, because if we're looking at one variable, then all we have is basically just lambda x. So it's not really that big a deal once we just get to one variable. But what we want to do is look at what happens, is what these representation matrices look like for x over these modules. So what happens if we multiply these by x? And what happens is we get this sort of this matrix where we have zeros everywhere except for the subdiagonal. We have ones on the subdiagonal, and others may choose to represent them. You can, take this basis, and I think you can flip it the other way. And if you do that, then you'll get ones on the super diagonal, which is something people might be a little bit more used to. And of course, so and then we just decided to call them Jordan blocks because of course they have that pattern. They're Jordan blocks. So we're just going to denote each of them as J sub I, right? Depending on which. So for a D2, the Jordan block would look like J2, okay? Or its matrix would look like J2, essentially. Okay, so. Okay, so, and of course, so yeah. So we have that these Jordan blocks are just I by I matrices, or J sub I is I by I matrices with ones on the subdiagonal and zeros everywhere else. So this is of course what D1, the representation matrix for D1 would look like, one for D2, D3, so on and so forth. Okay. And so there's nothing at the bottom. And so again, the question we want to ask ourselves is, if we do know the decomposition for some A modules M and N, then the question is, what does the decomposition for M tensor N look like? And that's something that we would need to use, or I guess it would be very helpful to use the matrices just so we can get more of a visual. Okay. So let's say hypothetically I have a M with this decomposition, I have N with this decomposition. When I do M tensor N, and I'm tensoring over K, that's an important part in this whole thing. Since I'm tensoring over K, we do have that M tensor N is also an A module, so it should have a decomposition as well. The question we want to ask ourselves is basically, can we write some kind of explicit formula for each of these L's, right? In terms of the M's and the N's and all that good stuff, right? And more in particular, we want to ask ourselves, what does a DI tensor DJ decompose as? Because if we know what this tensor decomposes as arbitrarily, then we know that tensor products and direct sums act nice enough with each other that we can move things around and figure out where everything's supposed to go. Okay. So, and of course, we assume that I and J are both less than or equal to P because we don't go past P. Time is it? Oh no. Okay. I knew I was gonna skip some stuff. Question is, which one am I gonna skip? Yeah, I'm definitely skipping all this. So what this part is essentially saying is, in order to sort of figure out how we're gonna go about getting this sort of about figuring out how we're gonna go about this process, we need to look at the group algebra structure of A, because there's a lot of work that's done in group algebra that allows that for group algebras that allow us to determine a lot of what's the best way to word this? There's a lot of things we can do over group algebras involving tensor products, and basically we want to essentially use the group algebra structure of A to allow us to do a lot of these things. So I'm gonna kind of go past this part. Okay. But also it also gives us a diagonal map for A, so that we're able to determine what what happens to like a baby tensor of A. So let's skip that part. And yes, so let me circle this. And so we get, so when we go through the process of working out the group algebra structure of A, and it actually turns out that A, that big truncated polynomial ring that we start off with, is actually has a half algebra structure, which is real cool too. Basically, we're able to take this, find a diagonal map that works to where if we take the diagonal of x sub I, that just, and I meant to get rid of those case, but this is just one this would just give us 1 tensor x sub I plus x sub I tensor 1 plus x sub I tensor x sub I. And then of course, when we just translate to one variable, this would just be 1 tensor x plus x tensor 1 plus x tensor x. This case. All right, so when we have our definition for this diagonal map for this delta, then we can use that to basically determine what our representation matrix for d sub I tensor d sub j will look like. And what it looks like is when it all corresponds, basically you take the identity matrix, the I by I identity matrix, and you take the Kronecker product of that with the representation matrix of x over d sub j, and then sort of flip the idea, plus the representation matrix of x over d sub I, Kronecker product with the j by j identity matrix, and then you add the Kronecker product of the two individual representation matrices. Okay, so it all kind of comes from that well, from the 1 tensor x sub I plus x sub I through 1 . I guess I don't need to put the i's. I'll just put x tensor x. Okay, so it follows directly from that. It's just now we're using matrices instead. And I think there's some kind of proof somewhere that basically shows that when you're doing tensor products on like linear maps and you want to show what the matrix looks like that represents it, I think the matrix just ends up being like the Kronecker product. So this sort of follows from that. So then we have that, of course, if we let M be some tensor product of these d sub i's, d sub I tensor d sub j, then, and recall that, of course, j sub I is going to be the representation matrix of x on or over d sub I, then we can derive the following formula. We can derive this as, we can basically replace all of these, the x's basically with their corresponding j's. So this one would be j sub j now. This one would be j sub I, and then of course we just have j sub I Kronecker j sub j, which if you wanted to write that out visually, what that looks like, basically all you do is you have j sub j's on the diagonal. So that's where this part comes from. And then you have these I sub j's plus j sub j's on the subdiagonal, which is all that put together. Okay. So let's just look sort of at an example of maybe seeing what one looks like, what a decomposition of some arbitrary ones look like. So let's say we consider the module M, D2 tensor D2, where we're just going to assume P is greater than 2. So it could be 3 or something. Then we just have that the representation matrix of X over that module is just going to look like I2 Kronecker product with J2 plus J2 Kronecker product with I2 plus J2 Kronecker product J2. So I mean, it's all just 2's in this case. But so then this matrix will look like this. So you have J2 and J2, which are just that and that. So it's just those two matrices right there. And then the I2 plus J2 is just the one in the corner. This one. Okay. And of course, when we put 0, the idea is this would be a 2x2 as well. So everything adds up. So then if we wanted to basically determine the Jordan canonical form of this matrix, that's probably something I should have mentioned earlier, is to be able to determine these decompositions, we're going to look at the Jordan canonical form of these matrices. And so to do that, we're just gonna kind of note that the only eigenvalue for this matrix is just going to be 0. So we're just going to take a look at the dimension of the null space of the matrix itself. And the dimension of the null space just ends up being 2, mainly because the rank ends up being 2. It's usually, this one is a little bit easier to see that the rank is just 2. So then you can just go back and say that the null is just 2 as well. So this just means that the Jordan normal form or the Jordan canonical form is going to be comprised of 2. There's going to be 2 Jordan blocks. And so with this particular example, we can just, if we figure out what the biggest one is, then we'll know what the other one is for free. And so by doing that, well, one of the easier ways to kind of go about this is, let's just look at what's happening with the powers and go from there, right? So if we square that matrix, we'll get this matrix right here, just zeros, and then there's 2 in the left bottom corner. And then if we cube it, or if we multiply it by x again, I guess, then we just get that it's the 0 matrix. So then we get that the minimal polynomial for this is just going to be, I put z because I think a lot of people normally put lambda, but I've used lambda a lot already, so I figured that'd be weird. So I just use z. I don't know if that's normal or not. But basically we get that our biggest Jordan block is just gonna be a 3x3. It's gonna be a J3. And then for everything to, match up properly, the other Jordan block would have to be a J1. So it just has to be this single block, this single 0 block down here. And then our J3 is up here. And so we have our Jordan canonical form is going to look like this. So as a result, our did I not actually put it? Oh, I should probably put it then. So our decomposition, so we had D2 tensor K D2, and this is just going to be, this is going to decompose as a D3 direct sum with a D1. Okay. So that's just what that decomposition is going to look like. Okay, I have a couple more minutes. So, okay, so these are some results that I've sort of gotten from the from this idea of what happens when you take an arbitrary DI and tensor it with a DJ. What does that decomposition look like? Bullets 1 and 3 are kind of sort of your extreme cases, sort of well-known cases. Well, so the first one is just because you're tensoring with a copy of K. D1 is just a copy of K. So anything if you tensor with a copy of K over K, you just get whatever this first thing is. So that's what the trivial one, I guess. This last one is sort of it's one of those things that makes sense, because basically what you're doing in this case is you're taking a free module and you're tensoring with some other module. And this just tells you that if you do that, then you should ideally just get a free module back. And so that's what's happening. You're just getting copies of DP back. Okay. And so this one's also sort of a well-known thing. And because of the fact that A originally, or that ring that we're dealing with, is a Hopf algebra, so it kind of comes from that. That's sort of a well-known fact. The middle one, that's something I figured out. I'm very happy I figured it out. At least I think I did. But hopefully this works. That we get that DI tensor D2 is just going to be isomorphic to a D1 plus I and a D1 minus I. So a direct sum of a D1 plus I and a D1 minus I. Okay, but this will only hold for I going from 2 to P minus 1. Because then, of course, if I ends up being P, then it'll fall in this category instead. Okay. And I think the other ones sort of follow a similar pattern. So let me sort of write some stuff down that what I think might happen, but I'm still in the midst of trying to actually figure out and prove and whatnot, is that if I look at a D3, or di d3. And so this is assuming that I is bigger than or equal to 3. I believe this one. Whoops. That's not what I meant to write. There we go. Should be a d sub I plus 2. Direct sum with, I believe it's going to be 2 copies. You do a D3, and that's of course running from where I is going to run from 3 to P minus 2, I believe, because it still has to be close enough. Okay. But that's still sort of working on that. All right. Ooh, it's 2:47. All right, so let's do this. That's so yeah, this is sort of a proof using the matrices, basically of the fact that you take something that's free, tensor with something else. So a DP tensor with DJ, and you should get something that's free. You should get J copies of the DP. And this is using the matrices to do that. And basically all you want to do is show that the rank of this matrix is P minus 1 times J, because that means that that its decomposition is only going to have J blocks. And the only way that's possible is if each of those blocks is a JP block or a DP block, if you will. Okay, so that's sort of what's happening with this proof. So I'll let you like to look at it. Slides will be up. And of course, there's a recording too. Yeah, that's a lot of fun. But yeah, it's a very drawn out proof. Oh, well, that's the end of the proof. And then there's sort of an example of what happens. Okay. And then the last thing I'll sort of mention, just in terms of future goals, is my computer is not okay. There it goes. Is obviously we just want to be able to figure out more cases for this particular problem, right? Can we figure out more decompositions? And also there's sort of a natural diagonal map that happens that's sort of I can't think of the word, but that's with A typically. It has a natural diagonal map that we did not realize until we had already found the other diagonal map. So, and basically we want to ask ourselves is when we come back to the Clebsch-Gordan problem, how does the decomposition differ if we use this diagonal map instead? Does the decomposition change? If so, how does it change? For the trivial case and for the free case, those shouldn't change. Those should stay the same. But for everything in between, who knows, right? They could be some could be the same, some could be different. It just varies. Personally, I think they're going to be the same, but there's no reason to believe, I think, off the bat that they should be. Okay. And then another thing we want to kind of think about is basically what happens if we remove prime characteristic P. So then what happens? So, what happens if we let characteristic of K be 0, for instance? Then, can we still get a lot of the same? Basically, if we take away the prime characteristic, a lot of the group algebra structure breaks down. So we can't do a lot of the same things we were doing before. So now we kind of have to use, instead of using K bracket U lambda, because that's not really useful once the characteristic is not P, then we'll consider this object, consider a hypersurface, and basically ask ourselves if an A module has a similar behavior over H that it does K bracket U lambda. And I would get more into that, but I think I'm out of time. So I think I'll stop right there.
Cool. Let's thank Kevin.
Thank you so much.
Questions for Kevin?
leave that open. Yeah.
Do you have any guesses for goal 2 of how using that map will affect the decomposition?
My thought process is I don't think it will. I think it'll make it easier for sure, because that last chunk, that exaby, tensor exaby, on the other diagonal map that we have causes a lot of issues when we're dealing with the matrices and stuff. And so I think using this one will make it a little bit easier. But I've done some cases with like D2, for example, and they've all pretty much been the same. And so I don't know if that'll keep going as I go up to D3 and D4 and so on. But I'm not, I don't think it's gonna change personally, but
Cool, thank you.
thank you.
Other questions? Francesca?
Kevin, I was wondering, what about other pieces of the alpha algebra structure, like the antipode map? Do
The
those give you?
Go ahead.
Yeah, do those give you something interesting too?
We haven't done a lot with the antipode. I don't believe I put it in this presentation, because the antipode, I remember when we were doing it, came out to be something really weird. But I think that's something we have to go back and recheck, but we haven't necessarily done anything with the antipode necessarily. I'm sure there's something that we can do, but a lot of our focus has been just dealing with the diagonal map. But that is something I could certainly go back and look at.
Thank you.
Thank you.
Other questions? Last call. All right, let's thank Kevin again.